Factoring special forms, and knowing when a quadratic can't be factored. In this video, we'll recognize when a quadratic expression cannot be factored. We'll recognize expressions of the form that's called the difference of squares and factor those, and we'll recognize a perfect square trinomial and factor that. Some quadratic expressions are not factorable. Let's look at this. For example, 10 has only two factor pairs. So if I want to make a quadratic, x squared plus bx plus 10, I only have two ways to do it. It either comes from x plus 1 times x plus 10, or it comes from x plus 2 times x plus 5. Now those two will give me a positive middle term. I could also have x minus 1 times x minus 10 and x minus 2 times x minus 5. They're just going to have the opposite middle term. Well, if I multiply out x plus 1 times x plus 10, I know I get x squared at the beginning and plus 10 at the end because that's what I was aiming for. In the middle term, we can do the little rainbow activity here. So x times 1 is x, and x times 10 is 10x, so I have plus 11x. And below here with the negatives, I'll just have x squared plus 10, but the middle term will be minus 11x. Again, if I multiply x plus 2 times x plus 5, the first term is x squared and the last term is 10. And the middle term is 2 times x plus 5 times x, or plus 7x. And the negative version will have x squared plus 10, but it will just have a minus 7x in the middle. Well, those are all the possible middle terms that end with a positive 10, and so any expression that doesn't have that middle term, x squared plus 8x plus 10, can't be factored because the only possibilities for 10 we have already explored, giving us middle terms of 11 and negative 11 and positive 7 and negative 7. Any other middle term will make something that's not factorable. It doesn't matter if it's not 7 or negative 7 or 11 or negative 11, it won't work. So there are many more non-factorable quadratics than there are quadratics that are factorable. So if you try all the factor pairs and you can't get the middle term you're looking for, that quadratic is not factorable. Binomials like these that differ only in the sign of the second term are called conjugates. And they have a special property because when they're multiplied, the middle term will cancel out. Positive 3x and negative 3x, that's just gone. And the resulting expression, although it's quadratic, it has a square, only has two terms, a square and a constant. Notice that the positive 3 times the negative 3 gives me a negative 9. An expression like this is called the difference of squares. The difference refers to the subtraction, and both terms, x squared and 9, are squares. The difference of squares always factors to conjugates. X squared has square root x, 9 has square root 3, and I factored back the difference of squares. Let's try and factor 4x squared minus 25. It's going to factor to conjugates, so it's going to have a 1 positive and 1 negative, and the first term will be the square root of 4x squared. So the square root of 4 is 2, and the square root of x squared is x, and both of the binomials begin with 2x. 25 has square root of 5, so it's going to be 1 plus 5 and 1 minus 5. So you can see that recognizing the pattern of the difference of squares makes factoring them much easier. And when you're recognizing the patterns, remember that the sum of squares is not factorable. If I square a binomial, it means to multiply it by itself. Exponents do not distribute over addition. So 5x plus 3 times 5x plus 3 gives me a first term that's the square of 5x. It's 25x squared. And then the last term is 3 times 3, so it's a perfect square too. It's plus 9. And how about the middle term? Well, I have a 3 times a 5 and another 3 times a 5. So basically I'm adding 15x twice. Now, if we analyze that, when I get all done writing it out, I have 25x squared plus 30x plus 9. I have two perfect squares, and then I have twice the product of their square roots. Let's use that analysis to factor a perfect square trinomial. So here we have 4x squared, that's a perfect square, plus 20x plus 25, that's a perfect square. So if this factors into a perfect square trinomial, the square root of 4x squared is 2x, that's going to be the same for both, and the square root of 25 is 5. And that's going to be the same for both. Everything has a plus. So what I need to do is check the middle term. 5 times 2x is 10x, and there's another 5 times 2x. It is 20x. So this factors to 2x plus 5 squared. Now if you look at this other one here, even though it starts and ends with a square, the middle term doesn't work out. It's not 20. On the other hand, it is factorable. If we use the AC method, 4 times 25 is 100, and factors of 100, 20 times 5, add to give me 25, 20 plus 5. If you split the middle term and factor by grouping, we end up with 4x plus 5 times x plus 5. So just because you see a square at the beginning and end of the trinomial does not mean it's necessarily a perfect square. You have to check the middle term. So we've talked about three different things here. One is that some quadratics are not factorable. If the factor pairs for the last term can't add up to make the middle term, there's no way to factor that quadratic. The second thing we learned was to recognize the difference of squares. An expression like 4x squared minus 25 is a subtraction, one perfect square, 4x squared, minus another, 25, and it factors to plus and minus the square roots of the two squares. So those are called conjugates, and that's how you factor the difference of squares. And finally, we learned to recognize a perfect square quadratic. It has the first and last terms as perfect squares, and it has the right middle term. The middle term needs to be twice the product of the square roots of the first and last. In that case, it factors. This one is 2x plus 5, the quantity squared.